Hello and welcome to my channel. Special welcome to those who are new to channel. So we will solve the next set of complex number problems in this video. So without further ado, let's get started. I did not get much time to work further on logarithm because I'm also busy writing my book. The book is available here. You see this red link. If you click this, you will be able to see the book. Okay. So it is free to read. You can download and read it. So let's get to slides. The book will contain all these problems which I'm discussing here. So you can download the book and read at your own pace. Now this is the 30th set of problems on complex numbers. So as always, I will repeat that when I am reading the problem, you should pause the video and try to solve the problem yourself. If you cannot solve the problem yourself, only then look at the solution and try to understand how it worked. So question 291 says find the set of all points on the xy plane whose coordinates satisfy the following condition. The number z square plus z plus 1 is real and positive. So we let z is equal to x plus iy, then the equation becomes x square minus y square plus x plus 1 plus iy into 1 plus 2x is equal to 0. So clearly the imaginary part has to be 0. So y is equal to 0. That gives us x is equal to minus half. Okay. So the real and positive, so it is real and positive for all points on the x-axis. So x is equal to half means it will be parallel to y-axis at x is equal to minus 2. When x is equal to minus 2, the real part becomes y square is equal to 3 by 4. Thus, for all the points x is equal to minus 1 by 2 and minus root 3 by 2 less than y less than square root of 3 by 2, the required condition is satisfied. Question 292 says that find the real values of the parameter a for which at least one complex number z satisfies the equality mod z minus az is equal to a plus 4 and the inequality mod z minus 1 less than 1. So the first equation, that is mod z minus az is equal to a plus 4, represents a circle whose center is at 0 comma ia and radius equal to square root of a plus 4. The second equation represents interior of a circle with center 2 comma 0 and radius unity. Now for the possibility of existence of z, the two circles must intersect each other. So square root of a square plus 4 less than equal to a plus 4 plus 1, that is a greater than equal to minus 21 by 0, and a plus 4 minus 1 less than equal to square root of a square plus 4, that is a less than equal to minus 5 by 6. So you combine this value and this value, you will get the range for a. Question 293 says that find the real values of the parameter t for which, the spelling is wrong, for which at least one complex number z satisfies the equality mod z plus square root of 2 is equal to t square minus 3t plus 2 and then equality mod z plus I square root of 2 less than t square. So we let x is equal to I plus x plus iy. Then mod z plus 2 becomes square root of 2 becomes square root of x square plus 2 root 2x plus 2 plus y square is equal to t square minus 3t plus 2. And mod z plus I square root of 2 implies square root of x square plus y square plus 2 root 2y plus 2 less than t square. But mod of z plus root 2 will be greater than 0. So t square minus 3t plus 2 would be greater than 0. That means t less than 1 and t greater than and t greater than 2. But for t greater than 0, both the equations are circles. So they must intersect for t to exist. So the distance between circles is the distance between centers is minus square root of 2 comma 0 and 0 comma I root 2. So the distance is 2 from these two things. So for circles to intersect, R1 plus R2 should be greater than 2. Now 2t square minus 3t plus 2 greater than 2. So that means t into 2t minus 3 greater than 0. This we got from the radius here and radius here. Therefore, t less than 0 or t greater than 3 by 2. And the second condition for intersection is R1 should be less than R2 plus 2. That is t square minus 2t plus 2 less than t square plus 2. That is t greater than 0. So combining all these inequalities, we see that t is greater than 2. Question 294 says that find the real value of a for which there is at least one complex number satisfying mod z plus 4i is equal to square root of a square minus 12a plus 28 and mod z minus 4 root 3 less than 1. So we let z is equal to x plus iy. Then from the first equation we have square root of x square plus 8x plus 16 plus y square is equal to square root of a square minus 12a plus 28. And from the second equation we have square root of 8 minus x square minus 8 root 3x plus 48 plus y square less than 1. But we know that mod z plus 4 greater than 0. So a square minus 12a minus plus 28 greater than 0. So x is either greater than 6 plus 2 root 2 or a is greater than 6 plus 2 root 2 or a is less than 6 minus 2 root 2 and a greater than 0. Both the equations are circles, so they must intersect for a to exist. So the distance between centers 0 minus 4i and 4 root 3 comma 0 is 8. So R1 plus R2 greater than 8, that means square root of a square minus 12a plus 28 plus a greater than 8. So a should be greater than 9. That is the value we get from this. And from the second condition for intersection, R1 should be less than R2 plus 8. That is a less than minus 9 by 7. So you combine these inequalities and you get a greater than 9. Question 295 says that find the set of points belonging to the coordinate plane xy for which real part of the complex number 1 plus I z square is positive. So we let z is equal to x plus iy. So 1 plus I z square is 1 plus I into x square minus y square plus 2ixy. Now real part of this is x square minus y square minus 2xy, which should be greater than 0. So from this we get two limits y into 1 plus minus square root of 2. Question 296 says that solve the equation 2z is equal to mod z plus 2i in complex numbers. So we let z is equal to x plus iy. We equate 2z is equal to mod z plus 2i. That is 2 into x plus iy is equal to square root of x square plus y square plus 2ixy. So we equate real and imaginary parts, we get y is equal to 1 and 2x is equal to square root of x square plus 1. So we square this, we get 4 square is equal to x square plus 1. That is x is equal to plus minus 1 by root 3. So we get two complex numbers, 1 by root 3 plus I and minus 1 by root 3 plus I. Question 297 says that 3 points represented by the complex numbers a, b, c lie on the circle with center O and radius R. The tangent at C cuts the chord joining the point AB at Z. Show that Z is equal to A inverse plus B inverse minus 2C inverse divided by A inverse B inverse minus C inverse C to the power minus 2. So earlier we have solved a problem where there are two non-parallel lines cutting the circle ABCD and their point of intersection was given by A inverse plus B inverse minus C inverse minus D inverse divided by A inverse B inverse minus C inverse into D inverse. So now in this case, the C and D will coincide. So in earlier case, we had a circle and the two chords were intersecting, one outside and one inside. That was the previous problem. Now in this problem, C and D coincide because it becomes a tangent. Okay. So the C cuts the chord joining ABC and at Z. So in this case, this C is a tangent. C and D coincide. So we put D is equal to C and we get the desired result. Question 298 says that show that all the roots of the equation a1 z cube plus a2 z square plus a3 z plus a4 is equal to 3 where ai less than equal to 1 is equal to 1, 2, 3, 4 lie outside the circle as origin and radius 2 by 3. So we have a1 z cube plus a2 z square plus a3 z plus a4 is equal to 3. So I remember we have solved a question like this. We take a modulus on left hand side and right hand side. We get a1 mod a1 z cube plus a2 z square plus a3 z plus a4. So from this we know from the identities we have studied that it is, this implies that mod a1 z cube plus mod a2 z square plus mod a3 z plus a4 is greater than equal to 3. So now we split the a1 and a2 and a3 a4 with the z. So we get this, that is mod a1 mod z cube plus mod a2 mod z square plus mod a3 mod z plus a4. This is greater than equal to 3. Now we know that mod a less than equal to 1. So this entire thing is mod z cube plus mod z square plus mod z plus 1 will be greater than equal to 3. Therefore, we can say that 1 plus mod z plus z, mod z square plus mod z cube to infinity is greater than 3. That implies that 1 by 1 minus mod z greater than 3. So mod z greater than 2 by 3, which shows that roots of the given equation lie outside the circle with center, origin and radius 2 by 3. Question 299 says that given that sigma I is equal to 1 to n bi is equal to 0 and sigma I is equal to 1 to n bi zi is equal to 0, where bi's are non-zero real numbers, no three zi's form a straight line. Prove that zi's are concyclic if b1 b2 mod z1 minus z2 square is equal to b3 b4 mod z3 minus z4 square. So we assume there is a circle at which we have 4 points a, b, c, d representing z1, z2, z3, z4. So from the second equation we have b1 z1 plus b3 z3 is equal to minus b2 z2 plus b4 z4. And from the first equation we have b1 plus b3 is equal to minus b2 plus b4. So we divide this equation from that equation, and we get b1 z1 plus b3 z3 by b1 plus b3 is equal to b2 z2 plus b4 z4 by b2 z4. Sorry, b2 b4. So this means that the point dividing AC, that is this, in the ratio b3 is to b1 also divides bc in the ratio b4 is to b2. So we let excuse me, let this point be O. So we have now b1 b2 mod z1 minus z2 square is equal to b3 b4 mod z3 minus z4 square. So from this equation we can write that b1 b2 b3 square plus b2 into b3 square plus b4 square minus 2 b3 b4 cos alpha is equal to b3 b4 into b2 square plus b1 square minus 2 b1 b2 cos alpha. Now from this we have b3 by b4 plus b4 by b3 is equal to b1 by b2 plus b2 by b1. This implies that b3 by b4 is equal to b1 by b2 or b2 by b1. Now if b3 by b4 is equal to b1 by b2, then b3 by b1 is equal to b4 by b1, which means AO by CO is equal to BO by DO. This implies that triangle AOB is similar to triangle BOC. Now if that is the case, then angle BAO is equal to CDO. Okay, BAO is equal to CDO. This implies AB parallel CD, which is not possible. Okay. All right. I was just referring to the problem. Now, if B3 by B4 is equal to B2 by B1, then AO by BO is equal to DO by CO. Okay. Now, this means that triangle ADO is similar to BCO. Okay. This means DAO is equal to OBC. That means ABCD are concyclic. Question 300 says that a cubic equation of x is equal to 0 has one real root alpha and two complex root beta plus minus I gamma. Points A, B, C represent three roots. Show that the roots of the derived equation f dash x is equal to 0 are complex if A falls outside one of the two equilateral triangles described on base BC. So we have three roots B, C and A. Okay. So we let fx is equal to k x minus a into x minus beta minus gamma and x minus beta plus I gamma. So we get the equation k into x minus a into x minus beta whole square plus y, gamma square. Now f dash x would be k 3x square minus 2 into alpha. This should be no, this is a, this shouldn't be alpha. 2 into a plus 2 beta plus b square plus gamma square plus 2a beta. Now discriminant of this would be given by 4 into a plus 2 beta whole square minus 3 beta square plus gamma square plus 2a beta. Now this is equal to 4 into a square plus beta square minus 3 gamma square minus 2a beta. Now if you look at this diagram, BC is equal to 2 gamma and PL would be square root of 3 gamma. Okay. If BC is 2 gamma, then PL is 3 gamma. Okay. you can compute it from here. Square root of 3 gamma, mod gamma. If A lies on inside the equilateral triangle, that is this equilateral triangle, okay, then if BC is base, then mod beta minus A is less than equal to square root of 3 gamma. So beta minus A whole square would be 3 gamma square, which implies A square plus beta square minus 3 gamma square minus 2A beta is less than 0. That implies this discriminant is less than 0. So the roots of the derivative would be complex numbers. With this, we come to the end of 30th set of complex numbers. There are roughly 70-80 more problems left on complex numbers. So we will finish complex number in 7-8 days. I may increase the number of problems, but may not, because I'm keeping the hard problems for the end when we will deal with miscellaneous exercises. The reason is that complex problems usually involve topics from more than one subject, like it may involve calculus, it may involve trigonometry or algebra altogether. So I hope that you have found this video useful and informative, and if you are new to the channel, please subscribe to the channel, and everyone please share, like, and make use of comment box to voice your opinion and speak your mind. For example, you can ask me to make more videos on some other subject like trigonometry or calculus, but I am continuing up in a very structured way, and once algebra is finished, I'll move on to trigonometry, then probably coordinate geometry or calculus, and so on. We will follow the entire syllabus of grade 12. So the reason why I ask for this like and subscribe is that the way YouTube algorithm works, if you like and share, then it reaches to many more people, and if you subscribe also, then it motivates me to make more such videos. So the reason for asking this is twofold. Thanks a lot for watching. Stay tuned for the next video. Enjoy.